All right. Well, thank you very much. Good afternoon, everyone. I realize the agenda is a little bit behind schedule, so I'll do my best to try to accelerate my presentation a little bit, but still give you all the information. My name is Jason Rios. I'm with Sentient Science, um, and I'd like to start by just saying how much we appreciate the opportunity to participate in this discussion and just share our perspective on the value of physics-based modeling in the scope of rotorcraft drive systems. Our session is going to explore the potential contributions of physics-based modeling and simulation tools for rotorcraft drive systems, yeah, for things like design, certification, qualification, potentially. But to also address the solution's abilities to conduct failure mode analysis or participate in failure mode analysis. And for the purpose of this demonstration or the purpose of this discussion, we're going to feature some examples from capabilities that we have internally within Sentient Science, just kind of as a demonstration of the use cases for physics-based models. So when we talk about physics-based modeling, the focus for us is on a first principles approach. And that basically means that we're basing our predictive outcomes on the physics of the designs, the loading conditions, the materials, etc., and not necessarily on a statistical analysis of big data. So why is this important? Well, fundamentally, components will break when their materials fail. And this is a behavior that can be modeled with physics and first principles to be able to predict the initiation of damage before it occurs versus kind of waiting for it to occur and show up on a sensor. And so that makes physics-based modeling an important tool in the tool set for forecasting fatigue life of drive system designs. Because really the capability to model the response at the material microstructure level is critical to understanding how fatigue failures are going to occur. And for rotorcraft drive systems, a fatigue mode of particular interest is rolling contact fatigue. So not so long ago, this capability was thought to be part of some kind of visionary future that would fundamentally alter how weapon systems and aircraft are designed. The U.S. Air Force chief scientist was looking forward to a time when advanced physics-based modeling and simulation tools would be made available to accelerate things like design, evaluation, certification, et cetera. But really, the fundamental contribution to these kinds of tools in the life cycle was to be able to find and fix latent defects at the earliest possible time in the development process. And then that has the ultimate effect of reducing the total cycle time for design, qualification, certification. So through the Small Business Technology Innovation Programs in the US, several agencies started to explore technology development opportunities to expand their insight into critical activities like drive system design and certification. So what you see here on the screen is just an example of one solicitation that came out. This one was from the U.S. Army, and they were seeking an improved capability to model the life of bearings, something that would incorporate the physics of the design, and also account for the microstructure level properties of the advanced materials that were being used in these bearings. So at the time that this solicitation came out, there was a feeling that the existing models didn't really provide that level of insight. And so it was through programs such as this that my company, Sentient Science, was able to develop a physics-based modeling capability for rotorcraft drive systems, which we call DigitalClone. And it's basically it's a physics-based modeling solution, and its focus is on predicting fatigue life, and it's applicable to both conventionally manufactured components and also to additively manufactured components. So we have capabilities to actually take additively manufactured components and digitally model and stress them in a virtual environment to be able to achieve the same fatigue life predictions that we're getting on conventional components. It's very well suited for things like rotorcraft and ground vehicle drive systems. And it's the result of a fairly extensive collaboration, not just with a variety of U.S. government agencies, but also as part of those programs, a lot of collaboration with airframe and system OEMs and the research institutes that had similar objectives. So this is just kind of a high-level look at the general modeling process. It kind of starts with this multi-body dynamic simulation. In this case, we're looking at a sample gearbox design. And in that environment, we're able to apply the loads and kind of isolate and identify critical gears and bearings. Once we do that, we kind of take it to the next step and drill down a little bit deeper. We focus on those critical gears and bearings and conduct a comprehensive dynamic analysis. And the purpose of that is to identify what we call the material hotspots, those critical locations on those key components that are likely to be the drivers of reliability or fatigue failures. Once we have identified those locations, then we go a level deeper and we kind of do a deep dive into the material characteristics in those hotspot locations. So we're able to, through a variety of material characterization tests, we're able to look at things like grain morphology, the quality of the materials that are being used in the components, looking at material defects, residual stress or micro hardness profiles, fracture toughness, and other key mechanical properties that relate to the types of failure modes that the system might see. In addition, we do an assessment of the surface roughness for components that are susceptible to rolling contact fatigue. So that takes us, once we have that information, we're able to move to the next step and build a representative volume element or a virtual microstructure model that is representative of the material characteristics that were identified in the previous step. And from there, we generate that microstructure in a virtual environment, and we have surface traction models that we apply as part of the solution that really unlock the ability of the solution to do things like predict rolling contact fatigue. So from there, once the model has been built, then we start virtually applying the stresses to that representative volume element, and we look at the impact of cyclic loading for things like rolling contact fatigue, and we apply a damage mechanics model to our approach that allows our solution to calculate kind of the cumulative effect of those stresses on the individual, grain boundaries within the materials. And this allows the damage mechanics model to predict the location and the type of failure that we would expect to see for these components. And so what the important thing about that is there's no seeding of faults. There's no artificially inserting a crack or a pit in a location in order to drive, the rest of the simulation. The location and the type of defect are a natural outcome of the running of the damage mechanics models. So that is, once we've completed that is just one iteration. Think of it as a single fatigue test or a single physical test. And so in most cases, it's valuable to generate an entire population of those kinds of tests, to repeat the process dozens or perhaps hundreds of times. And what that allows you to do is kind of create a virtual curve. And it's obviously infinitely more cost effective and faster than the equivalent physical testing. If you were to actually actually build these components and actually run them to failure on a physical test rig, it's pretty cost prohibitive and it takes a really long time. So this entire process that I just went over, we've productized it into a solution called DigitalClone for Engineering. And I won't take up a lot of time going into the details of the solution. Glad to talk to anybody that has interest in it, but I'll just give you kind of a quick overview of what's contained within the solution. And it's everything that we just talked about in that process, the ability to do kind of the multi-body dynamics to create like a geared system that's very suitable for rotorcraft drive systems to be able to do gear and bearing analysis, take into account material microstructure, and be able to look at design trade-offs. It has a built-in mixed EHL um, simulation or modeling capability to be able to look at the different impacts of various types of lubricants. And with all of that, you're able to kind of conduct virtual loading to be able to simulate operational conditions or to be able to simulate the test conditions of a physical test, say, for example, a qualification test, to be able to do risk reduction by being able to anticipate what you're going to see when you put that system on a test rig for qualification. So, and a very important part of our solution is this module that we call the Component Life Prediction, or CLP module. And what it does is it takes into account the various design or manufacturing choices, selections that are made by the designers in, whether it's a choice of base material or the shape of the gear tooth or the type of manufacturing process or heat treatments, etc. And we translate that into what the resulting property impacts would be, the measurables, the things like surface finish, grain structure, residual stress profile, hardness, material quality, etc., that are all really important to our modeling process. And you can see for a few of these, like surface finish, grain structure, material quality, you can see we've got this probability distribution kind of in the bottom right corner of that box. And that's just to indicate that those are properties that within our solution, we actually ensure that there is a level of randomness associated with those properties from one simulation to the next, because in reality, when components are built, even if it's a gear built in the same in the same manufacturing facility using the exact same processes, there's still going to be a level of randomness that's within the acceptable tolerances of the manufacturing process, but could still be significant when you are looking at the fatigue life performance of that particular component. And that's kind of what allows, if you look in the bottom right there, we've got an SN curve with scatter. That's kind of what allows our simulations to be more representative of what you would see in a physical test, is the fact that we are allowing for that level of randomness to be included within the simulations, because we think it is a fair approximation of what you would see in reality. And I'm not going to go too in depth on the actual specifics of the solution. We have a series of apps that allow users to easily create models using basic design information. So there's an app to create the bearings, and you can see it accommodates a pretty detailed, a pretty good amount of detail about the design of the bearings and about the shape of the roller elements. It allows us to account for things like the profiles of the roller elements, traction curves. We're able to look at contact pressures and slippage. We're even able to look at things like the bearing component microgeometry, excuse me, and the internal clearance changes, which kind of allows us to account for the differences, even for a specific bearing that's, two bearings that might be both built to the same ISO standard, but they're from different manufacturers, for example, or even different facilities. There would be those subtle differences in the bearings that need to be accounted for if you're really going to properly model the performance of that bearing design in a variety of applications. And so the solution allows for fairly detailed analysis that also provides visuals, time series, and custom plot capability for digestion of the results and be able to kind of use these results for analysis or risk reduction if you're looking at qualifying a design, for example. And we have the same similar capabilities, same type of app for gear analysis. Right now, the solution's suitable for spur and helical gears. We are also working on an enhancement to the solution that will pull in that's the same capability for spiral bevel gears. We know that's an important consideration for rotorcraft drive systems. But generally speaking, it's the same approach where we allow our users to use the app in order to translate their design information in a great level of detail to enable it to be pulled into the modeling and simulation environment. And we provide visuals that support detailed analysis of the performance of those designs under the loading conditions. And then once we kind of have built those at the component level, there's a very easy to use kind of drag and drop interface capability that allows the user to kind of build a system level model out of that. And that's obviously where a lot of the value is, to be able to look at multiple levels of fidelity, to really look at the components of interest, whether it's at a transmission level or whether you're looking at a specific ring gear and you want to see how it's going to perform under certain conditions. And that system analysis kind of allows for a more integrated assessment of how the individual components are going to perform. Where our solution enables users to actually create response surface models if that's something that they want to do, and actually generate a functional mock-up unit from the response surface models if they want to export these results into another environment, for example. So our solution is compatible with the FMI standard. So that kind of allows for the sharing of the results into other environments. And it does kind of have the built-in capability to enable design of experiments, to be able to look at a bunch of different trade-off analysis, for example. So, kind of at a high level, kind of coming back to our original objective, some of the insights that can be gained using physics-based modeling technology, like, something that Sentient Science has, it enables you to kind of get a really good understanding of the life impacts of certain design decisions and predict the performance of those systems in the qualification environment, for example, but also obviously looking forward into the future operational application of that system. You're able to kind of look a little bit further out and assess the impact of key design decisions, like the types of base materials you want to build your gears out of, what type of heat treatment process that you want to use in your manufacturing, the surface roughness that you want to establish as the standard for your gears. Even the type of lubricant that you want to use in the system. All of that contributes, if you are able to do it in a modeling and simulation environment, it contributes to kind of a faster, better, cheaper type of approach to taking those designs and getting them through qualification and out to the field and have a very reliable fielded product. So, and I like this quote because it's exactly what we're trying to do. We're trying to change the way that people look at things. And I've seen a couple of different attributions for this. Some say it's Dr. Wayne Dyer, some say it's Max Planck, but either way, I think it aligns well with what our philosophy is. And I'd like to just say thank you very much for your time today. And I'll turn it back over to our hosts, and thank you very much.